Okay, here we go. 10.1.2. Hopefully yesterday went okay. Hopefully you called me or emailed me if you had any questions. And here we go at 10.1.2. Confidence intervals for a population mean when the standard deviation is known. So population mean means we're going to be dealing with all X bars. And then remember I told you this was going to be a luxury I was going to take away from you. So in this case, we know the standard deviation. How can we calculate confidence intervals for any given level? So yesterday we only talked about 95%. Now, why does it have to be 95%? The only reason we used 95% yesterday is because it was an easy place to start, because we know the 68, 95, 99 rule, and 95% is 2 standard deviations away. So that was just an easy one to start with, but we should be able to do it at any given level that we want. So that's what we're going to do today. Told you it's going to get very repetitive. You're going to check these things 100 times between now and the end of the school year. So you must check these conditions before you do anything with confidence intervals, okay? So every single time, you need to know that it's a simple random sample. That is because we have to follow the principles of making a good study. So basically, if they didn't do a simple random sample, if they stood out in front of Burger King and did a crappy sample, we're going to have crappy results. Don't calculate anything. It's pointless. So every single time you're going to check that. Second thing you're going to check always is going to be this right here, which means either they need to tell you that it's normal, so they must tell you, or central limit theorem. So, or it needs to be big enough that we know that it reaches normality. Or actually, one more thing, you can check it for yourself, and you're going to see that in our example that we do at the end of the notes. And you AP testers out there, and actually you will have to do this on your test too, so I'll remind you how to do that. And then the third thing, and this is kind of a 2-for-1, you need to check 2 things here, or it's kind of a one or the other thing. So either you need to know for sure that everything is independent, and this is intuitive. Either depending on the situation, whatever it is, I need to know that every free throw is independent, or every part that I make is independent. Or if you're sampling without replacement, so like if you're drawing cards, type of thing, you need to know that the population's at least 10 times as big. So if you're not going to replace, you need to know it's a really, really big population. So you're going to check, and I would probably always just check both just to be sure. You're going to check independence, or you're going to check your rule number 1. And if you remember what rule number 1 is, it is that I'm totally drawing a blank here. Oh, duh. Population 10 times as big. So that the population is greater than or equal to 10 times whatever your sample is. Okay? So yesterday in the notes, I kind of skimmed over it, but we can pick any confidence interval we want. So in this example, we're going to do 80%. 80 is pretty low. So there is no perfect confidence level. You can do anything that you want. But obviously, if you're going to go out and publish a study, you don't want to say, I'm 80% sure this is going to help you. You want to say, I'm really, really, really confident. So typically, you should never go below 90%. That's just a general rule. If you're going to publish something, you want to be pretty sure about it. But in this example, we're going to use 80 just to show you we can use anything that we want. So yesterday we said if the true mean is right here, we want 95% of the data to be within here. Today we want 80% of the data to be within here. So if 80% of the data is in the middle, that means 20 is on the outside, which means we've got 10% on each end. So that means I need to find these z-scores right here. I need to find that z-score, and I need to find that z-score. Now it's going to be mirror image, so if you find one, you can automatically know what the other one is. We call that value right there z star. So however many standard deviations you want to be away. So if I know, if I'm going to look up for this z-score right here, then that means if there's 80% of the data here and 10% of the data here, that means there's 90% of the data over here. So if I want to find a percent, I have to go to the middle of the table. Do you remember this? So if you go to the inside of the z-score table to look up percents or proportion, and I want to find 90% because that's how much is going to be below this line right here. So 90% is somewhere between these two right here. Pick whichever one's closer. This one's only off by 3. This one's off by 15. So I'll take this one right here. So there is the percent that I'm looking for, which means that corresponds to a z-score of 1.28. So that means my z-star value is 1.28. So 80% means I'm going to go 1.28 standard deviations above, and it means I'm going to go 1.28 standard deviations below. Okay, so yesterday we said we're going to go 2 standard deviations above and 2 standard deviations below because it was convenient and it was a good place to start. Today we can do anything we want. So we find the percent that we want to use, and we're going to go 1.28 standard deviations above, 1.28 below. Now this gives you a fancy formula for it, but I wouldn't think that hard. Basically what they're saying is if I have 80 in here, I take 100%, minus 80%, and that gives me 20%. We know that. That's not tricky. So I know there's going to be 20% on the outside. I chop it in half to figure out how much is going to be on each end. You do not need a formula for that. I know you can all do that in your head, so you can just ignore that drawing right there. Okay, so that's going to give us our critical z-star value. That's going to tell us how much above and below we want to go, and we can pick whatever we want, typically over 90%. Now, here's the formula for it, but again, let's not think too hard about this. We can do this in our head. So if you remember yesterday, we had a mean of 112. That was what we figured out. And we said by the 95% rule, that meant 2 standard deviations above and 2 standard deviations below. So we added 2 times, was it 2.1? And then we subtracted 2 times 2.1. Because 2 standard deviations away, here's our standard deviation, so we wanted to do 2 of them, so we did 2 standard deviations away. That's what this formula says. It says you're going to take your mean, and then you're going to add and subtract however many z-scores you want to be away. So this is just the standard deviation formula that you know from chapter 9. This is however many z-scores you want to be away. So in the case that we just looked up, if we want to be 1.28 standard deviations away, then we take our standard deviation and we times it by 1.28. And we add that and subtract that from both ends, and we can do a confidence interval of any size that we want. Okay, so let's do an example together. Pause the video, open your book to page 630, read through the example quick, and then come back and we'll do it together. Okay? So, also when you're looking at that, look at the inference toolbox that's on page 631. That's what we're going to refer to all the time. These are the steps that are going to get very, very repetitive. So, step 1 says, always decide what your population is in question and decide what you're trying to find. So in this case, our population, and I gotta hurry up, I'm running out of time again. I gotta talk faster. Our population is all the video terminals produced in a day. So all terminals, and I'm not gonna write as much because then the video will go too long. So you can write that down. All video terminals produced in one day. What are we searching for? We're searching for the true mean of 20. So if a sample size of an n equals 20, we're trying to find what the true mean is for tension on the screen. So the true mean tension of the screens. That's what the problem's about. Okay, so after we decide what we're looking for, we're going to verify our 3 conditions, and you're going to add one here, independence. Because remember that last one is kind of a 2-for-1 deal. So first of all, is it a simple random sample? Yes, they told us it was. So you can go back and reread. They did tell you it was. Is it normal? They did not say anything about normal. So we have 3 choices, remember. Either they have to tell us, we have to be able to apply the central limit theorem, and 20 is kind of shady. That's not, it's on the limit, so we can't necessarily go central limit theorem. Or we have to prove it for ourselves. And this is how you're going to prove it. This is the quickest way right here. You're going to go back and put the data into L1 and L2, and you're going to do a normal probability plot. This is from the beginning of the year. Remember, normal probability plots should be roughly linear. You could also look at the box and whiskers plot, and it should be pretty much even. You could look at a histogram. You could look at all your graphs, but this is probably your quickest and most reliable one. And you will have to do this on your test. You'll have to just make a really quick sketch to show me that you looked. So if we look at this, it looks about normal. Check. We know that for sure as well. Now, number 3 said check your population and check independence. Now, this is where we think about it. I know every terminal I check has nothing to do with the one before it. Each terminal has its own parts, its own component. It's not going to break just because the last one did. So I do know that they're independent, but I am not replacing. I'm not taking one out, putting it back in, taking one out, putting it back in. So I should check the population as well. And yes, there are more than 200 terminals made in a day. They make millions of terminals, I'm sure. Okay, so step 3 says decide what you're going to do and make your calculations. So the problem asked us to calculate at a 90% confidence. So 90% confidence means, I'm trying to go fast so you can pause it and slow it down, but I don't want to do 2 videos here. 90% confidence means that if 90% is in here, then how much is on each wing? We got 10% left over on each wing, or on the outside, which means there's 5% here and 5% here. Agreed? So if I want to find this z-score, I need to go to the table and I need to look up where 95% is at. So pause the video and go do that. Go look in the table and see what you get for 95%. And you should get a z-star of 1.645. So and the only reason I take the 5 is because it was perfectly split between 2. You could pick 1.64, you could pick 1.65, but if it's perfectly in the middle, we can just tack that 5 on there, which means that this is negative 1.645. Okay, so I make my confidence. Well, X bar, you're going to have to put them into L1. I mean, they give it to you if you read through the example, but put them into L1, go to your 1 variable stats, and see what your X bar is. Your X bar would have been 306.3. Find the standard deviation for a sample size of 20. We're going to go to L1. We're going to find our standard deviation from the 1 variable stats, and you would have got 43. And then we're going to, or did they give it to you in the problem? They might have given us the 43 in the problem. You're going to divide by, I think they did. Divide by the square root of 20 because the sample size of 20, this is from chapter 9, and we get 9.615. Okay? So now I take my z-star and I want to be 1.645 standard deviations away. So I'm going to times this by 1.645 because that's how my standard deviations away I want to be. So I have an X bar of 306.3 plus or minus. I want to be 1.645 standard deviations away times the standard deviation of 9.615. And if I do that, this is going to be 306 point, crap, I'm going to run out of time. All right, I'll have to come back